The topic which we're going to discuss today is UV and visible spectroscopy. Visible light is a form of energy. Visible light is a form of energy. According to the wave theory, light travels in form of waves. It was believed that radiant energy is emitted by fluctuation of electric charges and magnetic field. There are various, similar to light, there are various forms of electromagnetic radiations, such as ultraviolet, infrared, X-rays, radio waves, etc. All of them, they are electromagnetic radiations. The peculiarity of electromagnetic radiations is they're produced by oscillation of electric charge and magnetic field residing on the atom. The electric and magnetic components are mutually perpendicular to each other, and they are coplanar. They are characterized by the waves. These waves are characterized by wavelength and frequency. The energy carried out by electromagnetic radiations is directly proportional to the frequency. Thus, electromagnetic radiation is a type of energy that is transmitted through space at an enormous velocity. Radiant energy has wave nature, as was already proposed. And according to wave theory, these radiations travel in the form of waves. They have wave nature. The energy of these waves is equal to h nu. It's directly proportional to the frequency, or E is equal to hc upon lambda, inversely proportional to the wavelength. E is equal to h nu, where h is Planck's constant and nu is the frequency. In the second equation, E is equal to h c upon lambda. Nu is 1 upon lambda. Frequency is inversely proportional to the wavelength. Come to the electronic spectrum. The arrangement of all types of electromagnetic radiations in order of their increasing wavelength or decreasing frequencies is known as electromagnetic spectrum. The visible spectrum represents only a portion of the electromagnetic spectrum. If we arrange all the electromagnetic radiations in order of the increasing wavelength, then portion above the visible region is called infrared, while that below the violet region is called as ultraviolet. Infrared radiations have longer wavelength and are less energetic. Although all types of radiations travel as wave with the same velocity, yet they differ from one another in certain properties. The arrangement obtained by arranging various types of electromagnetic waves or radiations in order of the increasing wavelength is known as electromagnetic spectrum. Just look at the visible light. It occupies only a minuscule of the electromagnetic radiation. Visible region just covers only a very minute part of electromagnetic radiations, that is in the wavelength region of 400 to about 800 nanometer. Ultraviolet has got the smallest wavelength, while red has got the longest wavelength. This is the spectrum of the visible region, which are violet, indigo, blue, green, yellow, orange, and red. On to spectroscopy. It is a measurement and interpretation of electromagnetic radiations absorbed or emitted when a molecule or atom or ions of the sample molecule move from one energy state to another energy state. It may consist of atomic spectroscopy or the molecular spectroscopy. In atomic spectroscopy, the changes in energy takes place at atomic level. For example, atomic absorption spectroscopy, flame photometry, whereas molecular spectroscopy covers changes in which the changes in energy takes place at molecular level. For example, UV visible spectroscopy, colorimetry, infrared spectroscopy, and so on. Absorption spectrometry. It's defined as the measurement of absorption of radiation energy by various substances. It involves the measurement of absorptive capacity of the radiant energy in the visible, UV, and IR region of the spectrum. When the molecule absorbs ultraviolet or visible light, its electrons get promoted from ground state to higher energy state. In the ground state, the spin of electrons in each molecular orbital are generally paired. While in case of higher energy states, if the spin of electrons are paired, then it is called singlet state. If the spin of electrons in the excited states are parallel, it's called excited triplet state. The triplet state is always lower in energy than the corresponding singlet state. This was something regarding the absorption spectroscopy. UV visible spectroscopy is a sort of absorption spectroscopy. In UV visible spectroscopy, this is an it's used in analytical chemistry for quantitative determination of different analytes, such as transition metal ions, highly conjugated organic compounds, and biological macromolecules. The spectroscopic analysis is commonly carried out in solutions, but sometimes solid and gaseous states can also be studied by UV visible spectroscopy. Solutions of transition metal ions can be colored because d electrons within the metal atoms can be excited from one electronic state to another. The color of metal ion is strongly affected by the presence of other species, such as various anions or ligands. The color of dilute solution, for example, the color of dilute solution of copper sulfate is very light blue. But when ammonia is added to it, the color intensifies and the wavelength of the maximum absorption, that is lambda max, is attained. Organic compounds, especially those containing high degree of conjugation, also absorb light in the UV or visible region of the electromagnetic spectrum. The solvents for such systems may be ethanol or certain other organic or certain other solvent in which the organic compound is solved. Solvent polarity and pH also affects the absorption spectrum of organic molecules. Charge transfer complexes also give rise to color. The colors are often very intense in case of charge transfer complexes. Thus, UV visible spectroscopy is a sort of absorption spectroscopy. It uses light in the visible and adjacent regions, that is ultraviolet region also. In this case, the spectrum of atoms and molecules undergo electronic transition. UV spectroscopy is concerned with the absorption of radiations in the range 200 to 400 nanometer. Valence electrons absorb the energy, thereby molecules undergo transition from ground state to the excited state. The absorption is characteristic and depends on the nature of electrons present. Several types of electrons are present. They may be sigma electrons, pi electrons, or n electrons. And the transition of these electrons from ground state to higher state give rise to the electronic transition. In case of methane, CH4, where there are all sigma bonds, CH bond only can undergo sigma-sigma transition and shows absorption maximum at 122 nanometer. The usual spectroscopic techniques cannot be used. This technique cannot be used below 200 nanometer. In case of sigma-sigma transition, it's a very energetic process because sigma bonds are very strong bonds. The organic compound in which all the valence electrons are involved in the formation of sigma bonds do not show absorption in the normal ultraviolet region. For saturated compounds like methane, propane, and other alkanes, absorption occur near 150 millimicrons. Sigma to sigma transition requires energy of very short wavelength. Very high energy is needed for such transitions. Next is the pi to pi star transition. This type of transition occurs in unsaturated centers of the molecule in compounds containing double or triple bond, that is, where there are pi electrons present. The excitation of pi electrons requires smaller energy because they are loosely bonded, and hence such transitions occur at longer wavelengths. A pi electron of double bond is excited to pi star molecular orbital. For example, in case of alkynes and carbonyl compounds, cyanides, azo compounds, etc., where there are pi electrons. Next is N to sigma transition. Such type of transition takes place in saturated compounds containing a hetero atom with unsaturated pair of electrons, that is, non-bonding electrons are present there. Such compounds undergo N to sigma star transitions. For example, are halides, alcohols containing the heteroatom O, Halides contain the heteroatom halogen. Ethers containing heteroatom O, aldehydes, ketone, both of them contain O as a heteroatom. Such transitions require comparatively less energy than that required for sigma to sigma transition. Finally, there are N to pi transitions. N to pi star transitions. In this type of transition, an electron of the unshared pair on the heteroatom gets excited to pi star antibonding molecular orbital. This type of transition requires less amount of energy. Low energy N to pi star transitions occur at about 290 millimicrons to 180 millimicrons respectively. Absorption occur at lower wavelength, and absorptions are usually very intense. So these were different type of transitions which were possible when an electron absorbs energy and is raised from lower state to higher state. Then there are chromophore. Chromophore is defined as the nucleus or any isolated covalently bonded group responsible for absorption of light radiations. Any group which exhibit absorption of electromagnetic radiations in the visible or ultraviolet region and intensifies is known as chromophore. Some of the important chromophores are given in the table. C double bond C, C double bond O, NO2, etc. These compounds absorb light of wavelength between 400 and 800 millimicron and appears colored to the human eye. Exact color depends upon the wavelength of light absorbed by the compound. Originally, a chromophore was considered a system which is responsible for imparting color to the compound. For example, nitro compounds are generally yellow in color. Nitro group is a chromophore which imparts yellow color. Similarly, aryl conjugated azo compound is a chromophore which provides color to the azo dyes. Chromophore in which the group contains pi electrons, they undergo N to pi transitions are ethylene, acetylene, etc. While the chromophores which contain both the pi electrons as well as the N electrons, they may undergo two types of transitions, that is pi to pi star and N to pi star. Examples of such type of chromophores are carbonyl compounds, nitriles, azo, etc. So chromophore are just the functional group which intensifies the color. Then there is another term known as oxochrome. These are coordinatively saturated or unsaturated groups which themselves do not absorb radiations, but when present along with the chromophore, they enhance the absorbing property of the chromophore. They are also known as color enhancing groups. All oxochromes have one or more non-bonding paired electron pairs, such as NH2 having a heteroatom N, OH OR, COH, etc. They intensify the color by extending the degree of conjugation. Thus, the non-bonding electron is shared by the conjugation, and thereby it affects the lambda max. For example, in case of aniline, group NH2 acts as a chromophore, but anilium ion hole acts as a the NH2 group in case of aniline enters into the extends the conjugation of the benzene ring, thereby it acts as an oxochrome. There are important laws which govern the UV visible spectroscopy. The Beer-Lambert law, it relates the attenuation of light to the properties of the material through which the light is traveling. The law is commonly applied to chemical analysis and is used in understanding the attenuation in physical optics of photons, neutrons, or rarefied gases. A common and practical expression of Beer-Lambert law relates to the optical attenuation of a physical material containing a single attenuating species of uniform concentration to the optical path length through the sample and absorptivity of the species. According to Beer law, when a beam of monochromatic radiation is passed through a solution of absorbing species, the intensity of beam of the monochromatic light decreases exponentially with increasing concentration of the absorbing species. That is, dI upon dC is directly proportional to decrease in the intensity. Whereas the Lambert's law states that the rate of decrease of intensity of the monochromatic light with thickness of the medium is directly proportional to the intensity of the incident light. That is, the decrease in intensity with time is directly proportional to the concentration. Sorry. Yeah, yes. For a particular wavelength, absorbance is equal to epsilon B into C, where B is the path length through which the light has to travel. C is the concentration, and epsilon is the molar absorptivity coefficient in centimeter square molar inverse. A is equal to minus log T. T is the transmittance, whereas A is the absorbance. A is equal to log I0 upon IT is equal to epsilon 0 B into L, which in turn is equal to minus log T. There are certain limitations of the Beer-Lambert law. That is, this law is obeyed only at a lower concentration. When solute and solvent form complexes, or they enter into a sort of association, this law does not obey. Or when the concentration of the absorbing solution is very high, again the law is deviated. At higher concentration, the law deviates from the straight line, and I've shown only the negative deviation. If the straight line turns upward, it's a positive deviation. So deviation occurs. Deviation can be found at higher concentration. Beer-Lambert law is applicable only at a lower at lower concentrations only. At higher concentration, the molecules may undergo association, thereby deviating from the straight line behavior. The law is not valid in case if the absorbing species is coagulated. The law also shows a deviation if the absorbing material contains certain sort of impurities. Apart from the chemical deviations, there may be instrumental deviations. Thus, this was all about the Beer-Lambert law. Beer-Lambert law and the by looking at this graph, there is a certain wavelength, that is lambda max, at which the absorption of light by the absorbing solution is maximum. That is known as lambda max. Lambda max tells a lot about the nature of the organic compounds, whether there are heteroatoms present, or there are pi to pi transition, sigma to pi transition, or n to pi transitions. A lambda max from the UV visible graph speaks a lot about the organic compounds. Kindly unmute yourself, and if you have any questions, please do ask.